So we just finished up lesson 2.2, which discussed and talked about linear equations. Now we're skipping lesson 2.3 because it relates to something that you would have already covered in Algebra 1 anyway, called direct variation. But I want to definitely spend some time discussing linear equations as they relate to real-life examples. One of the reasons why linear equations are so important is that because we have quite a lot of ways in which linear equations relate to the real world. And so we're going to be talking about word problems, and we're going to call these linear models. Trying to come up with a linear model or a linear equation to match a real-life word problem, something that could happen in real life, okay? And there's two types of word problems, or two types of problems that are going to give us different information. Depending upon what information they're giving us, is going to determine which way we go about setting up these linear models. So in all of these examples, what we're going to do is we're going to read a word problem and we're going to come up with the linear model that represents it, the linear equation that represents the situation. Then we'll be asked, after we come up with the linear model, then we'll be asked to find a given value, okay? And so we're going to look at the easiest one first. And the easiest one is if the word problem gives us the y-intercept and the slope. Now, in the case of a word problem, they're not going to call it the y-intercept and the slope, okay? But what you're going to recognize from the word problem is the y-intercept is your starting point, okay? What is given, where does the story begin? And then the slope is called the rate of change, okay? So let's talk about this on the inside. When we are looking at a problem, okay, we're going to be asked to take a given situation and we're going to be asked to turn it into some sort of linear equation, okay? So we're always going to write these equations in slope-intercept form, okay? So for example, all of these equations are going to be looking something like this. Now, something to mention. Because I mentioned to you on the previous page that the y-intercept is the starting point of the story, okay? You could also technically write it in this order. We have a starting point and then something changes. Let's talk about the rest of the steps, and this will make sense as we write it. You're going to read the word problem twice. The first time you're going to read it, you're going to find what number tells where the story began. Okay? What did the person, what did the thing, where did the thing or the person begin? What did they have at the beginning? Where did they start from? There's a beginning somewhere, okay? That value is going to be written in the equation, slope-intercept form, for the b. The b is your starting point. Okay? That's kind of why sometimes it's preferred to look at it this way, because it makes sense that the b is the first thing beginning with. It really doesn't matter what order you put it in. It's the same concept. Okay? After you find out where the object or the thing began, then you're going to do it a second time. Okay? And when you do it a second time, or read it a second time, you're then going to find the number that tells how the story how the story, you're going to read the problem and find the number that tells how the story changes. What changes in the story? Does something become more? Does something become less? How does it change? And there's two ways in which an event could change, okay? One way that it could change is that it could go up, okay? You began somewhere and then from there the value goes up. Or it could go down, okay? So for example, let me give you a real easy example of what we're dealing with here. Let me give you just verbally an example. Most people, when they have a cell phone bill, they have an amount that they pay per line on their phones, okay? And then, depending upon whether or not they have unlimited data, sometimes they're going to have to, when they text somebody, pay for the texting. You pay per text. So, if you're going to be paying per text, that's how the story changes. You have a set amount that you begin with every month that you have to pay no matter what. That's the beginning part. That's the fee to have that phone, okay? The part that changes, or the part that, affects what happens, is how many texts you send per month. That's going to add a number to your original amount that you began with, okay? When the story changes, that number is the slope. That's the M, okay? How will you know which one is which, okay? Well, sometimes you could just read it and figure it out, but there's also some really easy ways. Sometimes you're looking for some clue words that will give you a clue where the rate of change is. Anytime that you see anything like this, feet per minute, words per minute, seconds, like inches per second, okay? Anything that has 2 units like this indicates the rate of change. But you also might just actually see the words per, or, oops, that must be a quotation, per, or you might see the word each. If you see those words, the number that is with those or associated with those is going to be your rate of change, what is being added to it or what is being taken away from the original starting point. Let's look at some examples, and this will make it a little easier, okay? Look at the example here. A hot air balloon begins, there's a clue word for your starting point, begins descending, so it's already been in the air, but when it begins to descend, it descends at a rate of 20 feet per minute. That's what the slash means. So there's your word per. That indicates your rate of change. Where does it begin descending from? Well, it says from an elevation of 1,350 feet. Okay? So what are my variables here? Well, I always have to have an X and I always have to have a Y. Y is your elevation. Okay? Your elevation is affected by something. It's affected by how many minutes you descend, right? If you descend for a longer period of time, your elevation is going to drop, right? Descending means coming down. So X is the number of minutes that you have been descending for, okay? And another way of thinking about this is the X is my independent variable. Your independent variable is the thing that you control. I control how many minutes I'm descending, right? If I don't want to descend, then I put more air and I stay steady where I'm at. But if I want to descend, I let air out and I slowly come down with the balloon. I control that. If anything that you control is your independent variable. The elevation is your dependent variable because the elevation depends on what you do with the air, okay? Am I going to allow it to descend, or am I going to keep air filled in it and not descend? So the dependent variable, the elevation, depends on what you do per minute, okay? What you're doing with the air. So how do I write this as an equation? Well, we always want to write it in slope-intercept form. So it's going to be y equals mx plus b, right? Okay, what's my beginning point? Where did the hot air balloon, where did it begin descending from? What was its elevation at the moment when it's decided, hey, I'm ready to go down? Where was it at? Well, it tells you a hot air balloon begins descending from an elevation of 1,350 feet. So that's my starting point. That's my B. And I like to just I like to go ahead and leave the B first because this makes sense. If it's the starting point, it should come first. Now, what is happening in this scenario? Well, first of all, it's descending. If you're descending, are you going up or going down? Well, you should know that descending means going down. Ascending would mean going up. So I'm going down. So that tells me already that my rate of change or my slope is a negative. So I'm going to put a negative in there because you know that if you're going down, that's going to be represented by a negative number. Okay? Descending means going down. How much is it going down? Well, it's going down 20 feet per minute. Well, the variable that represents minutes is x. So right here is my linear equation, or you could write it the other way, y equals negative 20x plus 1,350. You could write it that way, okay? Still in slope-intercept form, okay? But to me, it makes more sense to keep your starting point first. So that's why I prefer to write it this way. Okay, so once I have the linear model, once I have the linear equation in place, I can be asked to find different things. I could change the amount of minutes that I am in the air for, or the amount of minutes that I am descending. And if I take the number of minutes, every time I add a minute, I descend 24 more feet downward. Okay? So if I increase the number of minutes, that's actually going to make the elevation decrease. Okay? So the value of y is actually going to go down every time that you add more minutes. Okay? And then the other thing I could do is I could say, okay, how many minutes would it take to reach a certain elevation? Y represents the elevation. So if I want to know, okay, I'm trying to get down to the ground, I want to know how long this is going to take me. Okay? Well, in that case, you'd basically be saying, well, how long does it take to get back down to zero, right? Or at least back down to where you took off, which might be above or below sea level. Okay? But the point is, you're trying to figure out how long it's going to take you to go to a certain elevation. Okay? So you can approach this in two different ways, and you could plug in different variables for different values for different variables. So let's see what B says. B says, what is the elevation after 20 minutes? Well, y is the elevation. I want to know what is y going to be after I have already been going down for 20 minutes. So I'm going to take my x value, which represents my minutes, and I'm going to put in a 20 there, because every time I go another minute, I have basically gone down another 20 feet. So if I go down for 20 minutes, I'm going to be multiplying that by negative 20, because I'm going down 20 feet every single one of those 20 minutes. So if I go ahead and solve this, I'm going to get 1,350. You know what? Let me make this a little smaller. Hang on. I'm going to kind of squeeze my equation in there a little bit better, so I have a little bit more room. So I'm going to basically be taking 1,350 minus 20, and then I'm filling in a 20 for the minutes. Okay? So when I do this equation, and you can use a calculator if you need to do these big numbers, negative 20 times 20 is negative 400. So I'm basically going to be subtracting off 400 feet from the 1,350, because that's how long, when I'm in the air for 20 minutes, that's going to make my elevation decrease by 400. So if I do 1,350 minus 400, I'm going to get 950 feet. So after 20 minutes, I will have descended from 1,350 feet down to 950 feet. Okay? So in this example, it was asking me to find the elevation after a certain amount of time. Now look at C. C is not telling me the same thing. C is asking me, how many minutes will it take? How long will it take the balloon to fall to an elevation of 500 feet? Well, y is the elevation. So in this linear equation, I'm going to fill in 500, not for the x, because I'm not talking about 500 minutes. I'm talking about 500 feet. I want to go down or descend to 500 feet. And I want to know, how long is it going to take me to arrive at that elevation? Okay? So what I'm going to do here is I'm going to solve this equation. I'm just going to have to solve it for x this time. So what you probably need to recognize is that in order to solve this equation, I'm going to need to subtract off everything except getting the x alone. So I'm going to subtract 1,350 from both sides. Now you probably are going to recognize it's going to give me a negative. And it's not really possible to have a negative number of minutes, okay? But it's not going to stay negative for long. 500 minus 1,350, that gives me negative 850. But on the other side, I have a negative 20x left. Well, guess how I solve for x? Well, I'm going to divide by a negative 20. So that's going to make the negatives over here on this side cancel out. So then I just have to find out on the calculator what 850 divided by 20 is. So if I do 850 divided by 20, I'm going to get that x equals 42.5 minutes. So remember, x represents minutes. So basically then, I'm just basically deciding, or what I've just found out is, if I want to go down from 1,350 feet down to 500 feet, that already is going to take me 42.5 minutes. So to get down to 0, it's going to take you a while. Hot air balloons don't move fast, okay? They're not descending very quickly, okay? They're descending very, very slowly. So it's going to take you quite a bit of time just to drop from 1,350 down to 500. It's going to take you 42.5 minutes to make that happen. So when a linear model gives you the starting point and it gives you the rate of change, it's just a matter of taking that equation and plugging it right into slope-intercept form. Okay, that's what this is. Y equals m, or mx plus b, or y equals b plus mx. For the purposes of doing word problems, I prefer to do it this way, simply because it makes sense for my starting point to go first. Okay? Now, in the next video, we're going to talk about what if it doesn't give you the rate of change? And what if it doesn't give you the starting point? Okay? How can we find out those values? This one takes a little extra steps involved. Okay? So we'll look at that in the next video.